My name is again Roberto Calandra, and together with Carol Hausman, we will be sharing also these keynotes. So it's my great pleasure to introduce Jeff Clun. Jeff is an associate professor of computer science at the University of British Columbia and a researcher manager at OpenAI. Previously, he was a senior research manager and founding member of Uber AI Labs, which was formed after Uber acquired a startup he helped lead. And Jeff's research focuses on deep learning, including deep reinforcement learning and robotics. So the talk he's going to give today is about improving robot and deep reinforcement learning via quality diversity, open-ended, and AI generating algorithms. So please join me to welcome Jeff. You are a little bit.
Can we increase the volume?
Hello, everybody.
Yes, please. If you can increase the volume, it would be great.
I'm going to share my screen. See that, Roberto?
We see a Google page. About feed loop.
I think if you just change to the other tab where you have your presentation, that should work.
Can you see my screen the slides now? Okay, excellent.
Yes, now
Thank
we
you.
can
Sorry
see.
about the technical issue. I want to thank the organizers for the invitation. It's wonderful to talk to you today. So today, the goal of my talk here is to do some work that I think will be unfamiliar for many of you, and that is
Jeff, excuse me, could you stop for 1 second?
And that is quality diversity algorithms and open-ended algorithms. And then
Jeff, sorry, could we increase the volume on your side, maybe?
Might accomplish our grand advantages, including producing like API, and that takes us down a path of a paradigm that I call AI. So that will take us into some deep dive into projects we've done that you can see here. Before I do that, though, I want to do a shout out to my new long-term collaborators across the art of
Jeff,
all
sorry, can you hear me?
today. And then Jean-Baptiste Moret, Ken Stanley, and Joel Raymond. And these are these really wonderful, brilliant
Can we contact Jeff
scientists,
somehow?
and I can't recommend more than take a deep look at their work and basically read everything that they've done. Sorry, Roberto, I can't hear you.
Can you raise the volume? Could you raise the volume?
I'm going to open up the chat. We increase the volume. How is it?
It also seems like you're using the
Jeff.
wrong mic.
Jeff, your
Seems
microphone
like you're
on
using
your computer
laptop
doesn't
mic
work
instead
very
of the
well.
mic in your
Can you
headset.
please change it so we can hear you? Your audio is very bad.
Now we can't hear you at all.
Very difficult, and I can't hear what people are saying. Is this better now, Elizabeth?
Not really. The volume is still very.
Third option. How about this? Is it better?
We still can't hear you.
Jeff, could you please use another source of microphone that is not working?
No, still can't hear you. If you could maybe look at your sound settings.
At the bottom left, there should be the possibility of choosing the audio setting from the Zoom folder.
Maybe if our technical people could help on the chat so that we could communicate with Jeff. Oh yeah, it looks like your mic is muted. Maybe you just need to unmute yourself.
Jeff, we just can't hear you at all. You've got no microphone.
On the Zoom call itself.
Yeah, so if you go to your sound settings, you should be able to choose a different microphone to the microphone you had
Right,
before.
we'll try to resolve it and be back in a second.
Is this better now? Can you hear me? You can hear me now. All right.
Yeah, much better.
Oh, excellent. Now I can hear you too, which is infinitely better. All right. Are we ready to begin?
Yeah, technical support. Are we ready to go again?
Right, Jeff, can you try saying something now?
Yes, I can hear you.
Yes, this is way better.
All right, everybody in the room, I really appreciate that. I hear you in applause. This is fantastic. I can hear myself echoing. All right. All right. I can hear myself echoing back in the room, but I will just try to ignore that. Is that possible to cut my own feedback from the room?
Can we do that?
Oh.
Can we cut the feedback?
All right. I think we're good. Okay. Somebody on Zoom, give me a thumbs up. Roberto, can you hear me still? Excellent. All right. I'm going to begin again. I apologize. I did have a lot to get through, so I'm going to try to just give my normal talk, and that might take us a little long. I hope that's okay with the organizers. So let's take this from the top. I apologize, but my name is Jeff Clune. I'm very happy to be here. Thank you for bearing with us for the technical details. And I want to thank the organizers for the invitation. Oh, I probably need to share my screen again, right? Let's do that. Can you see my screen? Excellent. All right. Perfect. So the goal of today is to tell you about some work that you may not be familiar with that represent different approaches to reinforcement learning and robot learning, including quality diversity algorithms and open-ended algorithms. At the very end, I want to then take a step back and think about how we might accomplish our grandest ambitions as a field, including producing AI generating algorithms, or via this new paradigm that I'm calling AI generating algorithms. So this work is going to take us into a deep dive into these projects that you can see here under each of these subjects. So before I do that, I want to give a shout out to my long-term collaborators, Jean-Baptiste Moret, Ken Stanley, and Joel Lehman, who have been with me throughout the development of all of the ideas and a lot of the work that you'll see in this talk. And I really just want to recommend that you take a deep dive into all of their work and read basically everything that they've done, because I think they're fantastically brilliant scientists and whose work is really, really, really important. I also want to quickly mention that I have a lot of ground to cover in this talk. And so I'm only going to briefly mention connections to some other work that happened before and after the work that I'm presented. But if you look into our papers or you want to chat about it with me offline, we do a deep dive into the literature and the connections to other work. All right, so there's a paradox in life, which is that if you try too hard to solve a problem, you're going to fail if that problem is very, very hard. But if you ignore the objective, you're more likely to succeed, ironically. So as a metaphor for that, imagine this maze. If you're down here in the start situation and you're trying to go toward the goal, and you only reward agents to get closer to the goal, well, then you end up with a plot that looks like this. Most of the agents go north and they get stuck in this dead end here. But if you only try to go somewhere new and seek novelty, then you end up trivially exploring and solving this maze. Now, it turns out that this is actually true for technological progress as well. So imagine if you had this cooking technology millennia ago, and you were the king or queen, and you said, I will only fund scientists who can improve the ability to cook food fast and with less pollution. Well, then you would never invent the microwave, because to invent the microwave, you had to have been working on radar technology and notice that a chocolate bar melted in your pocket. Similarly, if you had the abacus and you said, I will only fund inventions that produce more compute, then you would get maybe longer rods and more beads, but you would never invent the modern computer, because to do that, you had to have been working on electricity and vacuum tubes, which were not invented because they improve our ability to perform computation. And so the conjecture here is that the only way to solve hard problems may be by creating problems while you solve them and goal switching between them. So goal switching comes from this paper we had in 2016, which is when you're trying to solve one task, and then if you start making progress on another task, you shouldn't throw that out, but you should start pursuing that task in addition. So if you're a scientist and you want bipedal walking, and all of a sudden your robot starts to crawl or balance on one leg, you shouldn't throw that out because it doesn't measurably improve your ability to walk immediately, but you should embrace that serendipitous discovery and say, I want to start optimizing for that goal as well. And so we want our algorithms to capture such serendipitous discoveries as they occur within search. So that brings us to this new subfield of machine learning called quality diversity algorithms that my colleagues and I are developing. And the idea here is to produce a diverse set of high-performing agents, as nature does, as you can see here on the right. And so the most popular algorithm in this field at the moment is MapElites. And I want to recognize Jean-Baptiste Moret's leadership on this algorithm here. And the idea is actually really simple. So first, what we're going to do is we're going to pick some dimensions of what biologists would call phenotypic diversity, ways that the solution can be different. And we are going to discretize that space. So here in the example, we're going to have height and weight, but it could be speed, energy consumption, safety, whatever you want. And then once you discretize that space, then we're going to run first, we're going to randomly initialize the algorithm. So you have a parameter vector that specifies your policy or your agent or your body or whatever. You evaluate it. You get not only the performance or the reward, which we have here in colored, but also the height and the weight. And you put it in the appropriate cell. And then you run a very simple loop, which is grab something out of this archive, perturb it a little bit, reevaluate it, find out the new location according to those phenotypic dimensions, and if it's the best thing you've ever seen in that cell, swap it in. So basically, you're just keeping the best you've ever seen in each one of these locations. And so in traditional machine learning, you run an algorithm on a problem, and you'll get the highest performing solution found with some random phenotypic properties. But here, MapElites is very different. It's going to return you an entire set of solutions, which is the best you've found at each point in this hand-designed space. So we applied this to this problem of soft robotics. And even before MapElites, we had shown in this paper here that you can get some really interesting diverse solutions, but there's a cheat here, and that is the only way we got diversity was with separate runs of the algorithm. Within each one of these runs, there's not a lot of diversity. They're basically variants on one of these themes. And so the question is, can we get all of this diversity kind of within one run of the algorithm? So we chose these dimensions, which is the percent of this dark blue material, the number of voxels. And if you run classic optimization here in evolutionary algorithm, what you see is very low performing points. If you add diversity in this particular space, you get higher performing points. There's some yellow dots here, but it's surprising how little it searches the space, even though we're specifically adding a reward for being diverse. In contrast to that, MapElites is just a total sea change in what you get from an algorithm. It fans out and illuminates the entire search space and shows you, for example, where different local optima are. And interestingly, it often finds a better max performing solution because it is better at avoiding local optima. So what I love is to look inside the map and see the kind of diversity that you get. And what you see is because nearby points are similar, then you get kind of variations on a theme. So for example, if you go here, you take this creature on the bottom left that has almost no dark blue. And if you go vertically, you scan up, then you see more and more and more blue. Similarly, if you go over here, you'll see a creature that has a lot of blue in this bony shell. And as you scan down in this dimension, you see variations on that type of creature, but with less and less and less shell. So it's reminiscent of looking out into the animal world and seeing like all the great cats of different sizes and different colors, or the dogs, etc. So Another thing we found is that goal switching is critical in this process. So if you look, each one of these arrows here is a final solution in the map. And it's the beginning of the arrow is where the parent of that solution came from, because it was an evolutionary algorithm. And so what you can see is that oftentimes you need to make big leaps through the search space. So the stepping stone to get the best answer over here actually started off really far away. And if you look at an actual lineage of through time of where, if you take a final champion and you trace back where it visited in this map, what you'll see are these long circuitous routes through the space that you would never be able to intuit ahead of time or design ahead, say that's the curriculum I need to traverse in order to get to this final solution. But that is exactly what we see in the algorithm. So we took the ideas from quality diversity algorithms and we put them together into this paper in Nature that allowed robots to adapt like animals in about 1 to 2 minutes. And again, I want to highlight the leadership of Jean-Baptiste Moret on this project, as well as Antoine Colli. So here's our robot, and we're going to try to get it to adapt if it is damaged, even substantially so. So we took inspiration from animals for this project, because animals don't do what ML algorithms do. They don't just like brute force a lot of small variants to one particular policy until something works. Instead, they start out having intuitions about very different ways to move. And then they conduct a few intelligent tests and then pick a behavior that works despite that injury. So we're going to do that on this robot that you can see here. So to get intuitions about different ways to move, we're going to use the map elites algorithm. And we picked a 6-dimensional behavior characterization, which is the percent of time that each of these 6 legs touches the ground. And you can see the final result of that in this map here. And the original search space here is massive. It's got more solutions than there are molecules in the solar system. Map elites goes out and it collects all the high-performing gates that it finds until it gets a set of about 13,000 gates, which is still a lot, but every one of those gates is high-performing, and we know how they relate to each other, which is essential. So here, for example, is one of the gates, and this is a robot that uses that leg 10% of the time. And in another cell is the best gate that used this leg 10% of the time, and on and on and on. And what's kind of funny is that there was one literal corner case in this hypercube, which is we asked the robot to walk without touching any of its legs to the ground, which we thought was impossible, but nature will find a way. It figured out how to walk like that, which was pretty impressive. So now we have intuitions about different ways to move on the undamaged simulated robot, and now damage happens and we want to try to figure out how we can efficiently adapt. So we can use Bayesian optimization here that will conduct a few intelligent tests within this map, and then we have a simple stopping criterion for when we think we've got the best gate possible. So Bayesian optimization is great because the prior can come from the map elites from the undamaged simulated robot, and then BayesOpt can basically update that prior to create a new posterior in response to every test. So here's how it works. You have the undamaged tripod classic gate here. It's 0.25 meters per second, and it walks in a straight line. And then damage occurs, and that gate now no longer works. You can see that here. And so we launch the algorithm. And what I want to draw your attention to, first of all, is the clock in the top right corner. That is the real number of seconds of evaluation that have been occurring. And second, after we conduct that test, we update the colors in the map, which are the posterior prediction of the performance of these robots. And so what you'll see is every time we find that a gate doesn't work anymore, we can update all of the points that are nearby in the 6-dimensional space. And so you'll see colors changing throughout the map in this 2D projection. And we say, oh, that type of gate no longer works. And that means not only does that gate no longer work, but all gates like it, we probably think that don't work anymore. And then we can keep doing that a few times. And what you'll see here is after about 25 seconds of evaluation, we've now found a gate that has basically recovered the original performance, and it goes straight. And now we can continue on with our mission, which is a very efficient robot adaptation. So we conducted a lot of experiments to show that the algorithm works with different damage conditions, different behavioral descriptors on different robots, and also even that it can be used to adapt to different environments, which is quite exciting. And in all cases, the most important thing we found is that Map Elites is really doing the heavy lifting here. So if you run Bayesian optimization or policy gradient directly in the original search space, then you do not get very good performance. You really need those intuitions provided by the quality diversity algorithm at the front end. Also recently, somebody showed that all of these ideas carry through into the modern era with deep learning algorithms. So to conclude this chapter of the talk, I think this work shows the power of quality diversity algorithms to fuel other algorithms, here Bayesian optimization, and to produce robots that can adapt in less than 2 minutes. So the next project I want to tell you about also takes advantage of the ideas of quality diversity algorithms in a totally different context. And this is the algorithm called Go Explore, which was designed to deal with hard exploration problems in robot and reinforcement learning. And this was in Nature in 2021. So I think a grand challenge in RL is effective exploration. And that comes in 2 forms. You have sparse reward problems, where you very infrequently get any feedback whatsoever. A good example of that is Montezuma's Revenge, which kind of had become a mini grand challenge in the field of RL because all of the algorithms we have perform terribly on this type of problem. There's also deceptive problems where the reward function is actually lying to you. So in this game of Pitfall, for example, until you're very good at the game, almost everything you do results in negative points. You run into enemies, you fall down traps or holes, you lose points. And so every RL algorithm basically learns to stand still and do nothing because that's the only way not to get negative points. So if you look at the prior results, classic deep RL algorithms on these things get about 2,500 points max on Montezuma's Revenge and 0 or negative points on Pitfall. You can do things like run UCT or MCTS. They also perform terribly. And so surely you're thinking to yourself, well, we should try intrinsic motivation and, basically reward agents for getting to new states. And it helps a little bit, but basically it still leaves most of the game entirely unsolved. And so a couple of weeks before we put our first Go Explore paper on arXiv, there was a lot of fanfare and excitement about this new advance represented by R&D, which had improved over these previous low scores to get a score of about 11,000 on Montezuma's Revenge, which was a really big deal. I mean, it was a big step up versus what we saw before. But 11,500 still leaves a lot on the table in this game. So I think it's interesting to think about why is intrinsic motivation not working better on these hard exploration problems. And I think one reason is if you think of this situation, if an intrinsically motivated agent comes to this choice point and has 3 doors it can take, it might take the blue door and it opens it up. And sure enough, in that wing of the building, there's lots of unexplored places and it gets all this intrinsic motivation. But once its policy has figured out how to go deep into the blue wing of the maze and it runs out of new places to explore, it doesn't remember to come back to this door and take the other 2 doors. So we call this problem detachment. And I think this is a real pathology at the heart of exploration in RL. So imagine you're one of these agents and you're in the maze in the top left. Everything that is green, if you get there, is new to you and you will get intrinsically motivated to be there. You'll get a reward. And so the agent starts exploring the left maze, turning green into purple, and it gets pretty far, but we're randomly perturbing the policy because we're trying to do exploration as well. And so we eventually it starts flipping over and exploring the right side of the maze, and it consumes all of the green on the right side of the maze. But now think about what happens to that policy. It has recently been being trained to go to the right, and so that's all it knows how to do: go to the right, go to the right, go to the right. There's no green over there, so now it just starts flailing around in the space of white, not getting any intrinsic motivation at all, because it has detached from and forgotten about the promising area of green that it formerly knew about on the left side of the maze. So our proposal is to explicitly remember where promising locations are and how to get back to them. Another pathology, I think, at the heart of exploration in deep RL is what we call derailment. So imagine if you're an intrinsically motivated agent, you're exploring this wall here on the right, and you get all the way up here, which is really, really impressive, but then you fall off the wall. Now, what will most RL algorithms do? Well, they'll run the policy again, but they are always taking exploratory actions throughout the entire trajectory. So via epsilon greedy or posterior sampling and policy gradients, you are sampling and injecting noise while you're trying to get back to where you were, and most likely you'll fall off this wall because that was a really hard thing to do. And that problem gets exponentially worse as the length, complexity, and precision of the sequence increases. So we're actively hurting our algorithm's ability to explore. So our proposal is that we should first return to this location on the top right and then explore from it. And maybe we'll figure out that there's a huge jackpot on top of that platform. But we don't need to make it harder in that process of first returning before exploring. So you might counter that will hurt the robustness of the algorithm because we're not practicing in the face of stochasticity all the time, and I would agree. But remember, we're exploring. We don't know where the jackpot is on this wall. It might be on the left, it might be in the middle, it might be on the top. So our proposal is let's first figure out where the reward is and how to solve this problem, and then we'll just pay the cost of robustifying that particular type of solution. So we break things into two phases, an exploration phase where we first solve, and then a phase 2 where we robustify. So here's how phase 1 works in Go Explore. We're going to initialize the algorithm by taking random actions and storing the states that get visited in an archive. And then we're going to run this loop until we solve the problem. We pull a state from the archive, we go back to it with no added exploration. We just try to get back to it, and then we explore from it, say by taking random actions. And if we find new states, we add those to the archive. And if we get back to the same state, but in a better way, either we scored more points or it's more efficient, whatever you want to do, then we swap that in as the preferred path back to that state. Now, this should seem familiar to you because this is basically an application of the principles of quality diversity algorithms, but this time to getting to different states within a game. So the idea is that we want a huge diversity of states that we can get to in the highest possible performing way. So it's basically map elites in state space. So now I think now that you understand how the algorithms work, I think it's instructive to think about the difference between intrinsic motivation and Go Explore. So if you're searching a giant house, intrinsic motivation is having like a narrow beam flashlight that first you shine in one place, and then it gets drawn to a place you haven't been yet, and then drawn to another place you haven't been yet. But your policy is always myopically going to one area of the search space that is currently delivering intrinsic motivation. Go Explore, in contrast, is like turning the lights on in the living room of the house, and then their adjacent rooms, and then those adjacent rooms, etc., until the entire house is illuminated with this expanding sphere of knowledge. So we can't run this algorithm in the raw state space, it's too high dimensional, and so we need to do some conflation where interestingly similar states are considered the same cell, that's what we call it, and if you get to a new cell, you've gotten to a new type of state. So to do that, our first attempt has like very little domain knowledge. You just downsample the image, and if two images hash to the same downsampled frame, we consider that the same situation, and otherwise, we consider it a different situation. To choose cells, we prefer ones that have recently paid off in leading to new states or that we haven't tried a lot. To return to a cell, we have two options. If you're willing to use the fact that you're in a simulator, which you often are in RL or robotics, then you can just restore the state of the simulator and save those. If you're not willing to exploit that, then you can train a goal condition policy that gets back to a state that you have been to before. I'm going to start by showing you the stuff where we do restore the state and then finish up with the goal condition policy. So to explore, after we return to a cell, we can just take random actions and get to new states. So that leaves us with an algorithm that looks like this. In phase 1, if we're restoring from the simulator, we actually don't even need to train a policy. We can just end up with this open loop series of actions that ends up getting to the final reward. That's not going to deal with any stochasticity in the world, though, and that's what we really want is a policy that can deal with a stochastic evaluation. So then we switch to a phase 2 where we just use imitation learning algorithms. Like imitation learning algorithms that know how to learn from demonstrations. We give them the demonstrations from Go Explore, and they robustify that into a neural net that can deal with stochastic situations and generalize. So when we ran this algorithm, we ended up with something that was 4 times the previous state of the art, and it beats the human expert on this game. And you can see this dramatic improvement versus all of the work that had come before on Montezuma's Revenge. Now, my ideal algorithm does not require domain knowledge, like Go Explore did not, but if you give it to it, the algorithm can take advantage of it and profit greatly. And so the way that we can do that is we can just tell it what counts as an interesting cell representation. So instead of downsampling, we'll say, hey, every time you get to a new XY location, get a new number of keys or to a new room, then that counts as an interesting new cell. Now note, this is just for the exploration phase. The final neural net still plays directly from pixels without any of this information. When we did that, we actually got dramatically better results. So now on average, we score 660,000 points, and our best policies could basically play the game forever. And we even got networks that get a score of 18 million and beat the human world record on this game of 1.2 million. So this has really basically solved this problem of Montezuma's Revenge. We even beat previous work that was willing to take demonstrations from human experts because we could provide more demos and better demos. Here is a quick video. I hope that these work across the internet. And I won't show you this because I could run this for hours, but the agent is really kind of smooth in its play and it looks really natural, like a human expert would do. On Pitfall, I told you that no prior algorithm had ever scored greater than 0. Go Explore with domain knowledge is able to get on average 60,000 points. And so our best policies can basically get all of the points that are possible in this entire domain. We ran the algorithm on all of the Atari games from the benchmark, and in almost every case, we got state-of-the-art results, and in every single case, we beat the average human, which was the definition of success in the original DQN paper. And for all of the games that were unsolved and all the hard exploration games from Atari, we also paid the cost to robustify Go Explore, the policies, so we can do a really fair evaluation of them in the proper environment. And what we found is that Go Explore solved all of the previously unsolved games on Atari, and in some sense, therefore, retires this as a challenging benchmark for the field. Now, I promised you that if you weren't willing to restore simulator states from the game, then we have a policy-based version of Go Explore, which trains the network to go back to whatever state you want it to via a goal condition policy. That then deals with stochasticity throughout the process. And the benefit of that is that, one, you don't need a robustification phase, and two, you can also use that policy to explore more efficiently. For example, in Pitfall, you frequently have to solve the same type of challenge over and over again, and this algorithm can generalize and solve those the first time it sees them, as opposed to having to rediscover those skills. And so when we run that algorithm with domain knowledge on these two challenges, they dramatically improve the state of the art, and they beat average humans on the game, including beating a lot of previous methods that also took advantage of domain knowledge. So I think one thing that's really important for the room that I'm speaking to now in this conference is that I think Go Explore could be a real game changer for robotics. And I would encourage people who are interested to try to apply Go Explore and really push its limits, because I think it could do wonderful things for robotics. In robotics, we often have hard exploration problems, and we want to specify problems in a hard exploration way just to give the final thing we want done and not create this like staged cookie crumb process of all these intermediate waypoints. So we want to be able to say, like, find the survivor, put the item in the bin, clean up my living room, etc. There's like a really natural way to do that in Go Explore. So in a deterministic simulator, you can solve the problem, then you can robustify it in that simulator, and then transfer it to reality via some of these techniques here, and optionally learn in reality. So to demonstrate the power of this, in a simulated task, we have this robotics challenge on the left here. So the robot has to put these blocks away in one of these 4 bins. We give it a target bin, and it only gets a reward if the block is successfully placed in the bin, which is a very hard exploration task given all of the motor torques and stuff that it needs to actually act in. And if you see on the right here, policy gradients, even with intrinsic motivation, completely fails on this task, whereas Go Explore basically solves the task every single time. So I think the future directions here are very exciting, especially for robotics. The first thing we'd like to do is learn the cell representation instead of have to design it. I think that would allow us to learn what constitutes an interesting challenge in an arbitrary domain. And so I really encourage people to work on this, because nobody's cracked this yet, but I know that it's solvable. And I also think we could use Go Explore to produce generalists. So if you have 1,000 or 1,000,000 tasks, you could use Go Explore to very efficiently figure out how to solve each task. And now you've got 1,000 solutions for 1,000 different tasks, and you can distill that and robustify that into a general neural net that can solve a variety of different tasks. It got the demonstrations very efficiently. So to conclude this chapter of the talk, Go Explore represents a new approach for hard exploration problems. It opens many new exciting research directions. I think, once again, it shows the value of quality diversity algorithms in collecting a diverse repertoire of high-quality entities and then doing something with them once you have them. So I hope I've convinced you that QD is quite interesting. It produces this diverse set of high-performing agents or policies. It takes advantage of goal switching. It can conduct what we call a divergent search, which is to fan out and discover what's possible in an environment. So what's missing? And I think the answer is that, like all machine learning algorithms, or most of them, it's trapped within whatever environment we've put it in. And so if we're running it on Go, we'll only get a Go playing agent. If we're running it on StarCraft, that's all we'll get. And traditionally, that's how machine learning operates. We pick a problem, we run an algorithm in it, and when it gets really, really good at that, we move on to the next problem that we pick. But I think it's much more interesting to think about an algorithm that could pick the problems itself. So this brings us to an entirely new subfield of machine learning called open-ended algorithms that my colleagues and I have been working on for a long time, as well as others. And the goal here is to produce algorithms that endlessly innovate. I mean, forever. Examples are natural evolution and human culture, which innovate without bound. They never converge. They never run out of steam. They've literally been 3.5 billion years of evolution, and it's still doing interesting, novel, surprising things. And so the grand challenge that I would put in front of you and all of computer science is, can we make algorithms that do this? If you look at all the things that Tree of Life produced on the right, it did jaguars, hawks, and the human brain, and more. And our algorithms should be able to do that too. But to date, we've never had an algorithm that's worth running more than a few months. So how can we create an algorithm that's worth running for 1 billion years? That's the grand challenge. So nature, if you look to one of the key secrets it has, it invents problems and it solves them, and their solutions beget more problems. So arguably, nature produced the problem or the learning opportunity or the challenge of leaves high up in trees, and the solution to those problems in the form of giraffes and caterpillars. And then those solutions end up being opportunities for other things that can predate on them or live inside them or cooperate with them. So our first salvo at trying to produce open-ended algorithms, or I should say our most recent salvo, is the paired open-ended trailblazer or POET, which was done with these wonderful collaborators. And the goal here is in the subtitle of the paper, which is to endlessly generate increasingly complex and diverse learning environments and their solutions. So POET is quite simple, really. It periodically will generate new environments, and it will add them to this growing archive or set of environments if they're not too hard for the current population of agents, and they're not too easy for that population as well, and they're different than any previous environment that we've created so far. Simultaneously, we're optimizing agents to solve each of these environments and allowing goal switching between them. So if you're currently the best on this environment and suddenly you look really promising on some other environment, we'll make a copy of you and switch you to that other environment. So here's how the algorithm works. We have a parameter vector that specifies and describes an environment, phi1. We have a parameter vector theta1, which is a policy or neural net that will optimize against that environment. After it's good enough, we'll copy phi1 to make phi2. So now we might have a slightly harder environment. And then we will copy theta1 into theta2. And now we're simultaneously optimizing both policies on both environments. Eventually, we might try to create a new environment. This one might be too hard, so we throw it out. So we try again, we get a medium hard environment, and now we see whether or not theta1 or theta2, who's the best on this environment initially to seed that attempt at optimizing to that new environment. And then we basically repeat this process. It doesn't have to be a chain. We'll take any environment, potentially copy it. We'll check all possible policies to see who's the best to optimize on that environment. And we'll go on with this process. So imagine eventually we do this and we produce this really hard problem here, phi6. Initially, it looks like theta5 is the best seed policy to start optimization. So we start optimizing a copy of it. But there's an innovation that happens over here in phi4, and theta4 ends up becoming a goal switches over to phi3 and becomes the best solution to that. And then maybe it learns some new skill there, and ultimately it comes to replace theta6 and swap in, and now we have a totally different solution that maybe unlocks and finally solves this very hard challenge. So I want to show you some videos here. We ran this in this simple little bipedal locomotion domain. And what you'll see is every single environment you see was generated by the algorithm, and the solution was also generated by the algorithm. And so you see this little agent. Initially, the algorithm starts by having separate challenges, like rugged terrain or gaps to jump or stumps to walk over. And usually it starts by having the agent practice one of those skills separately, and the skills get harder and harder over time. So now this robot is kind of maxing out its ability to get over some of these stumps. But eventually the algorithm figures out it should start combining challenges. That's the next level of difficulty. And so here we ultimately get this agent that's able to jump really big gaps, cross really big stumps, and deal with rugged terrain all at the same time. So we took some of the final hard environments that this algorithm produced and solved, and then we tried to directly optimize solutions for those environments. And in every case, we failed, even though we used the exact same optimization algorithm. And that's because we didn't have a curriculum that could get you, bootstrapped up to learn those skills. And so you might say, well, that's cheating. You could just make a curriculum. So I say, okay, fine. We'll take some of these hard environments. We'll take the original easy environment, and we'll create an intuitive linear curriculum that interpolates between the parameter vector specifying easy environment and that hard environment, and then we'll just let agents move along that curriculum. And what we find is that in every single case, that fails. Eventually, there's a stepping stone that's too hard, a link in this chain that the algorithm can't cross. And so this really, I think, underscores the benefit of goal switching, where you don't want to try to intuit ahead of time what the curriculum is. You're probably going to fail. Instead, just let all the sorts of craziness happen, and eventually you'll get some wild path through the space that can solve these hard problems. So here you have the agent that is walking. This is one example that I want to show you. So on flat ground, you have this agent that is walking. It gets a score of 298, and it's dragging its knee. And if you eventually the algorithm creates a new challenge, which has these little tiny stumps, and it turns out that doesn't work for the agent. It is unable to get over these little stumps. And what happens is that eventually it learns to stand up in that environment, and with further optimization, it proves its speed quite a bit. Now, since we're always checking for goal switching opportunities, what we end up figuring out is that the agent gets transferred back into the simple environment. And now that it's stood up, it's much, much faster. It gets a score of 311. And with further optimization, it's off to the races and getting quite a high score, much higher than the original score. Now, we did the counterfactual here. We said, what if we hadn't transferred out to that other environment and come back? So we just take that original agent and give it tons of computation. And what we find is that it truly was stuck on this local optimum. It never learns to stand up, and it never learns to get fast. So here's an example of a curriculum that you would never invent on your own, because you'd never think you have to go work on a harder problem to come back and solve this easier problem. But in fact, that does improve performance. So I want to also share with you some follow-up work we had in this paper called Enhanced Poet. So the first thing we did is we wanted to really push the limits and give it a more open-ended environment search space. So we used a CPPN, if you know what that is, and you can see the different kind of challenges that are produced on the right. But the most important thing is that we invented this domain general metric of what constitutes an interestingly new environment. And so the insight here is, if you have any newly generated environment produces a new rank ordering of all your previous agents, then it must be doing something interesting. So, for example, imagine if so far you have a population of agents and they're diverse in some ways, and you have agents that hop on one leg. And so far to date, the agents that hop on one leg, they've never been the best on any environment. They're okay, but they're not the best. And you generate some new environment, and all of a sudden, all of the one-leg hoppers are now the highest performing and highest scoring agents on that environment. Well, I don't know what that environment is. I don't know what challenge it's putting in front of these agents, but I know that it has an interestingly new challenge because it has completely changed the ranks of the agents and is eliciting some new skill out of the agents that they're able to perform. Another thing that we did is we created a very generic measure of progress in open-ended systems, which is non-trivial because since you're not optimizing for a particular thing, it's hard to know when you get it. But what we figured out basically is that as long as the system continues to generate new environments that initially were not solvable by all prior agents, but come to be solved, then that is a healthy sign of progress. You're generating qualitatively new and interesting challenges that are able to be solved. So when you put all of these innovations together and a few others I don't have time to talk to you about, you get the red curve here instead of the blue curve. So original Poet had basically maxed out what was possible in its initial environment, where this new algorithm can keep going as far as we were able to throw compute at it. And I think this is really interesting because my entire career I've been searching for algorithms that don't converge, that don't run out of steam, that continue to do interesting things. And here is the first time I've seen an algorithm that has no humans in the loop, that just keeps going for as long as we're able to throw compute at it. I think another example of that may be AlphaGo and some of the StarCraft work. So I want to quickly show you some of the environments that were invented by this algorithm and solved. You can see the agent has solved all of these different challenges here. And if you zoom in on any one of these challenges, what you'll see is an agent is quite able to solve these problems and has learned a variety. The agents in this world have learned a variety of different skills, which is quite exciting. Here's one of my favorite. The system invented this giant cliff, which you would never think an agent could solve, but it hucks itself off the cliff and sticks the landing. Pretty fun. So here is a plot of the environments that are being generated over the time in this algorithm. And this is one of my favorite plots of my entire scientific career because I've been searching for this since I was a brand new PhD student. Every time we run algorithms that have evolving populations of agents, we do not get phylogenetic trees of sustained diversity. But now we're finally starting to do it with the ideas that I'm presenting in this talk. So here you have entirely different families of environments that are all related to each other, and then another family or clade or species or genera somewhere else in the population. They're being like riffed on and innovated upon, and you get all this diversity kind of bubbling up and staying around within one run of the algorithm. So right after we published Poet, we ended up, some other groups started using similar ideas to great effect. And one of my favorite is this example of Rubik's Cube solving robot from OpenAI. So they took similar ideas and they added in meta learning and a shared policy behind all of the environment. So one policy solving all these challenges. And what you end up with is an adaptive generalist. It can conduct a few experiments to figure out how the new environment is different from things that it has seen before, and then adapt based on that information and solve this problem. And what's really great is they showed that if you do that just in simulation, it can even do that and solve problems in reality, even though it was never trained in reality. Similarly, here's some work that was inspired by Poet on a robot that looks a lot like a Boston Dynamics robot, but this is with a learned solution to the problem. And I think it's so wonderful. This, a couple of years ago, this would have been science fiction in my mind. And now you see these ideas playing out and solving really, really difficult challenges out there in the real world. So that was very exciting. I think going forward, it gets even more exciting. I want to remind you, we all know it, but it's hard to internalize it. More cheap computation is coming, exponentially so. And so soon we'll be able to run Poet in environments that look as rich as this, with aerial predators, markets where you have to go trade and negotiate, people that might try to rob from you and steal from you. You might have to join a team, join a group and fight against other groups or cooperate with other groups, etc. And so I think the sky's the limit of what we can accomplish once we have Poet running like in this kind of environments. So to conclude this chapter of the talk, Poet shows the benefits of quality diversity algorithms, but also layering in the generation of challenges while we're trying to solve them. I think there's a lot of exciting possibilities going forward. And the main challenge here is, what is the search space we're operating in, and how can we make it tractable to search in that space? We want an environmental search space that is rich in that we can produce any of the challenges we want to produce, but is also tractable in that we don't get lost in that giant search space. So the overall, now I want to take a step back, and I want to think about the most ambitious goals of our field. Very briefly, I think that many of us, including Alan Turing, one of our founders, is interested in producing what we could now call AGI, artificial general intelligence. I think we have a long way to go, but I think it's interesting for us to think as a community about how we might get all the way there, not just to the next milestone 1 year from now. And I think if you look at most of the work in machine learning, it's what I call the manual path to AI. It kind of says, let's go identify key building blocks to AI. And if you look at most of the papers and most of the conferences, they either say, here's a new building block that we haven't had yet, or here's an improved version of an existing building block. I think that raises the question of how many more are out there, and can we find them all manually as we've been trying to do one by one? But even if we could, the manual path then has to deal with a phase 2, where you try to put all of these building blocks together into some very complicated thinking machine. And I think we should be clear-eyed about what a Herculean task that is. It would be very, very difficult to put all those pieces together, to get all the hyperparameters right, debug the system, etc. I think if you look at machine learning, what you'll see, though, is that there's a clear trend, which is that hand-designed systems ultimately give way to entirely learned solutions once we have enough compute and data. We've seen this with features, architectures, hyperparameters, data augmentation pipelines, and RL algorithms themselves. And that suggests an alternate path, which I call AI generating algorithms. The idea here is to learn as much as possible of all of the pieces to produce an AGI, and do that via an expensive outer loop that's searching over the space of agents to ultimately produce something that itself is very, very sample efficient at inference time. And we have an existence proof that this can work in the form of Earth. So on Earth, the very unintelligent, very expensive algorithm of Darwinian evolution produced the human mind, which is the most sample efficient, impressive learning agent that we're aware of. So if we want to make progress on this, we have to simultaneously push on 3 pillars. We have to meta-learn the architectures, meta-learn the learning algorithms themselves, and generate effective learning environments automatically. And I think handcrafting the solutions to each of these challenges would be very slow and would be limited by our own intelligence. So it's better to learn them and let machine learning and compute do the heavy lifting. So we've seen a lot of work recently on learning architectures. Neural architecture search is now a thriving field in our community. I think Kwok Lee and Esteban Real doing fantastic work at Google on this. And my group has done some work that you see here in purple in case you're interested in checking it out. In terms of meta learning, the learning algorithms themselves, I think we've also seen some wonderful work, especially in reinforcement learning. Recently, the wonderful work by Jane Wang on learning to reinforcement learn, as well as RL squared out of OpenAI. And my group has also done some work in this area, which you might be interested in check out, which is in purple. But this talk is really focused on the third pillar of AI GAs, which is to generate the learning algorithms automatically in a way that is effective. And so what I hope I've shown to you is both of this is the least explored area of the three pillars, and it's probably the hardest, and therefore I think it's, for me at least, the most exciting. And then I hope I've showed you that a lot of the ideas from quality diversity algorithms and open-ended algorithms can really shine a light and show us techniques that might help us move the needle on this really challenging pillar. And so POET and Enhanced POET represent our best attempt so far in pillar 3. There's also been some exciting work combining multiple pillars, so specifically pillars 2 and 3. I've already told you about the OpenAI work, which did that, and also recently Max Jederberg's team at DeepMind did some fantastic work on what they call XLand, which is an agent that trains on a huge diversity of tasks, and then these agents, basically can zero-shot end up solving really, really challenging, complicated tasks, such as capture the flag, hide and seek, and other games like that. So I really suggest you check out, work out, and it's very much the beginning of an AI generating algorithm producing general AI and agents that can generalize and do things like cooperate and communicate. And interestingly enough, that comes out of a team named the Open-Ended Learning Team at DeepMind. So the final thing I want to mention is that AI GAs, I think, are worthwhile even if you're not convinced that they're the fastest path to powerful intelligence. That's because I think they're intrinsically interesting. I think it's interesting for us to know how simple processes can bootstrap themselves into intelligence, what are the necessary, sufficient, and catalyzing factors, and creating simulations of that allows us to study those questions. But most importantly, it's just a fundamentally human thing to want to know how we got here. And these are the algorithms that could tell us about our origins, because we got here via something that looks a lot like an AI GA. In fact, we got here via an AI GA, which is Darwinian evolution. And that also sheds light on how likely this process is to work on other planets, to produce intelligence on other planets, and perhaps most interestingly, it could produce a wild diversity of intelligence that is not made in our image manually, but is discovered automatically by machine learning. And we could come to understand the broader space of intelligence and what it might look like in the universe. And almost it's like inventing the ability to have contact with alien cultures if we can get this to work. And imagine what we'd learn from these alien cultures that are created inside of our computers. So to conclude, I have introduced quality diversity algorithms, which I think are a state-of-the-art approach for exploration. They create and collect stepping stones. They harness goal switching to avoid local optima and capture serendipitous discoveries that occur within the algorithm. They invent effective curricula, including hedging their bets with multiple overlapping curricula where you don't know ahead of time what's going to be the right path through a space. And a lot of times those paths are very counterintuitive, which is why goal-oriented attempts fail. I've also introduced open-ended algorithms, where the goal is to create algorithms that endlessly learn and innovate, like natural evolution and human culture. And I think that if you figure out what are the key ingredients we're going to need for open-ended algorithm, it's going to involve ideas from quality diversity and probably generating environments automatically as well. But then I put a couple question marks here because we don't know what else is needed. The truth is we have no idea how to make open-ended algorithms now. And that, I think, is a call to arms for everybody in this community to start thinking about, because I think it's a grand challenge. I think there's a Turing Award and a Nobel Prize, or both, sitting out there waiting for whoever can make progress on these problems. So to conclude, and the final thing I introduce are AI generating algorithms, which I think are likely to be the fastest path to AI. The hypothesis is the pieces of AI are learnable, and the clear trend is that learned solutions ultimately win out over hand-designed solutions. And so I think that AI GAs could be the fastest path to AI for those reasons. They shed light on our origins, and they're also likely to be very creative and surprise us. And therefore, they're worthwhile to pursue, even if they're not the fastest path to AGI. So with that, I want to thank all of the collaborators that I've worked on, the funding sources, the organizers of this workshop, and all of you for your patience, especially at the beginning with the technical difficulties, and for listening. Thank you very much.
Thank you very much, Jeff, for the inspiring talk. We will now start with questions from the online chat. If anybody online wants to ask a question, please move to session Keynote 2 and ask a question in the chat. To give time, I'll start with the question I have. So when you were talking about all the quality diversity algorithms and math elites, it seems to be very similarly conceptually to multi-objective optimization, where you also want to sort of see what are the performance, create this sort of landscape of performance, and then choose from this. Do you have any, sort of idea about the relationship?
Yeah, sure. So we've done a lot of work actually comparing those kind of algorithms, which is a natural way to start on these problems, and quality diversity algorithms. And in short, quality diversity algorithms usually perform far, far, far better, at least in the kind of things that we want to solve, than those algorithms. And that's because those algorithms are fundamentally about trade-offs. You know, like what is the best trade-off between this thing and that thing? And you always reduce that ultimately to some scalar, which is basically saying like, you know, I want to be on the Pareto front of these possible trade-offs. And so everything kind of is still competing with each other, and you end up losing a lot of promising stepping stones that might be really interesting, even if though they're not on the trade-off. So one way to think about it is that in nature, if you had a trade-off between, say, speed and, I don't know, energy collection, well, then you probably wouldn't get the fastest ant and the fastest three-toed sloth and the fastest bear and the fastest frog, because they're not all Pareto dominant. But what we really want is we want ants and sloths and dolphins and bears. And then within that species, we want them to be high performing, but we really don't want them competing and precluding each other's existence, which tends to happen when you have these Pareto front-based solutions.
Okay.
All right, thank you, Jeff. We'll also have a question in person. Are there any questions here? I see some raised hands. Can we give the mics?
I'll read here a question online in the meantime. So how rich will the generated environment have to be? For instance, will they eventually follow the second law of thermodynamics, which is essential to life on Earth?
Yeah, so I think this is a wonderful question, and this is the question that probably I wake up thinking about every morning. And that is kind of, what are the key ingredients from the natural world that enable the explosion of complexity that we see there? And how much of the richness of the natural world and its physics do we need to get into our algorithms? We cannot have a planet-sized computer with the rich physics of the universe. And so if it's the case that we need to have all of the rich physics and the size of a planet-sized computer, then we'll never be able to do this. And so I think the goal for our field is to figure out what are the efficient abstractions of the key principles that unlock the power of nature and to get them into our algorithm. And so I think quality diversity algorithms are one example of that, where you don't say, I'm going to rely on one giant world and some rules of physics that's going to create a situation in which I can get an ant and a sloth and a bear. But instead, I'm going to have separate niches, and I'm just going to declare by fiat that whichever is the best at this niche gets to survive, and I'm not going to like rely on physics to protect that diversity. And so those kind of abstractions and innovations might enable us to shave, 5, 10, 20 orders of magnitude off the compute budget. And that's what we need to look for. And so every scientist should say, I think this is accidental, I'm going to leave it out. Or I think this is essential, I'm going to put it in, and then see what happens. And if we keep doing that and thinking deeply about what the key ingredients are and what the right abstractions are, it is my bet that we're going to be able to create open-ended algorithms that are many orders of magnitude more efficient than nature, maybe 10, 20, 30. And that, well, 30 is a lot, but that'll allow us to produce wonderful things in computer simulations without the rich physics of the natural world. But it's an open question. It's the one we have to all experiment with and think about.
Carol, do you
Right,
have
let's take the
questions in person there?
Yeah, let's take the question from here.
Hey, Jeff. Thank you for the talk. I just want to say I'm a huge fan of some of the ideas that you presented before I say what I'm about to say. which might be a little adversarial.
That's dangerous.
But so when you move away from like these gradient, like you mentioned using CPPNs and open-ended algorithms and like doing things like neuroevolution and genetic algorithms, you lose kind of that gradient information. And at the same time, like for example, doing backprop is intrinsically a human constructed, like biased solution. You would hopefully expect that like an evolutionary algorithm would be able to learn backprop in one of these open-ended environments. My question is, when you make these environments more open-ended and complex, a lot of the perturbations that you get from like an evolutionary algorithm are useless. So like for example, in natural evolution, a lot of the mutations that happen to like cells, for example, are like pointless and they don't really, well, not pointless, but they don't really do anything. And so it's kind of like one of the things we don't see in evolution is that it's actually brute forcing and we only see the solutions that work. So my question to you is, how do you, maybe have you thought about this, or how would you like rectify that? Would it be beneficial to kind of like introduce human biases to like make the search more efficient as you go towards more open-ended learning algorithms?
Wonderful question, thank you. So the couple things to note. One is that imagine for a second that nature is really unintelligent in how it perturbs things, and most mutations are terrible, and there's a lot of waste there. Well, that's one opportunity for us to gain many orders of magnitude versus nature, and so that's a good thing for us. And so we can, like you say, try to use our science, technology, our machine learning knowledge to generate better candidate solutions and not do it randomly and unintelligently, and maybe that helps speed up the process. Another thing is, though, that nature, it turns out, if you look at it, and I've spent a lot of my career studying this and experimenting with this, it actually doesn't do things as dumbly as you might think. There's this process called evolvability in canalization in nature, where actually over time, nature got more and more intelligent at generating intelligent candidate solutions in the next generation. So most mutations in nature are still deleterious, but far better than if you hadn't had this process that basically recognized the low-dimensional manifolds of successful solutions and tended to traverse those as opposed to doing things off-manifold. So just as machine learning recognizes, for example, in generative models, the low-dimensional images that recognize natural images and doesn't tend to generate a lot of garbage when you're, say, doing a GAN, evolution over time does the same thing. It recognizes the low-dimensional manifold of interesting solutions and things that are likely to be high-performing, and it tends to preferentially produce those. So one very simple example of that is symmetry, where most mutations produce symmetric organisms. So if you are a four-legged dog, mutations don't tend to produce one leg that's wildly longer than all the other legs. It tends to either make all legs longer or all legs shorter. And there's tons of examples in this. So to answer one of your questions, which is have I thought about this? I've basically thought about this every day of my life for the last 15 years. And so if you look, you'll see some papers where we've worked on the evolution of canalization. And I've also done some work with Richard Watson where we show that evolution is in fact like machine learning. It's generalizing from past experience to produce high performing solutions much better than random. And so I think another thing that we can do is, either we can say, let's try to recreate what happens there in nature to produce intelligent generalization, or let's use some of our tricks and techniques from machine learning to do that. But to your final point, should we kind of use human intelligence to do it? My bet is that machine learning is going to do a better job than humans. So what we need to do is create the stage in which the system can learn to be evolvable and canalize and do better, and let machine learning figure out how best to do that. And so I think, one of the simple ways to do that is to have networks that basically learn based on past experience what proposals are most likely to be successful and generate them. And it doesn't have to be an evolutionary algorithm. It can be a gradients-based algorithm that's doing all of that heavy lifting, and that's another way to be more efficient than nature.
Right, thank you, Jeff. We have time for one more question. Right, we have a raised hand over there.
Hiya, thanks for the talk. It was really nice. I have just one. I'm just curious about how AI generating algorithms would relate to genetic algorithms and things of this genre and how they could be applied to address the problem of AI generating algorithms, for example. I'm not sure if...
I'm sorry, I missed that. Can you say that again? How they relate to what?
So let me maybe repeat the question.
Thank you.
The question was, how do genetic algorithms how can they contribute to AI generating algorithms?
I see. Yeah. So one of the things that I really want to emphasize to this room is that it's not about evolution versus gradients. I think every time that I give a talk, because I'm one of the few people in our community that uses evolutionary algorithms, people really focus on that and they latch onto that and they think about that versus gradients. But all of the ideas that I presented today have nothing to do with an evolutionary algorithm versus a policy gradient algorithm versus, you know, a Q-learning algorithm or backprop, et cetera. And so I would really encourage you to look past the algorithm under the hood to the ideas, because the ideas here can and have been ported to and applied to a variety of different algorithms. But I'll still take the bait and answer your question. I think that one of the things that evolutionary algorithms have been shown to do is they can operate in search spaces where we don't know the best way to do it with gradients. So I think, you know, even the last question mentioned, you know, you'd love to see evolution invent backprop. But if you look at the work out of AutoML0 of Esteban Real and Kwok Lee, there is a situation where an evolutionary algorithm there did rediscover not only backprop, but dropout and ResNet connections and all sorts of kind of innovations that we've seen in the last few years of machine learning is being kind of rediscovered by the algorithm as it goes. And I think that's the kind of work that is really future facing, and we'll see more and more situations where whatever the underlying algorithm that is that you're using, you have a machine learning based approach where with a lot of compute and a lot of data, it figures out a lot of solutions that are better than anything that we can come up with. So basically, I think it's not as, you know, really it doesn't matter what optimization algorithm you use. You just want to be in a situation where lots of compute and lots of data can lead to a lot of creativity, diversity, and ultimately learn solutions to the grandest challenges of computer science and AI. Because I think ultimately, you know, we're not smart enough to create AGI ourselves, and we want to set the stage for machine learning to solve that problem. Just as we weren't smart enough to hand code the solution to computer vision and NLP, we had to use machine learning to learn that. So now let's apply that same paradigm and turn it to the grand challenge of producing AGI itself.
Right. Thank you, Jeff, and let's thank Jeff again.